All right. Here we go.
Yes.
Oh, here we go.
Yes.
There we go. All right. What we're really kind of doing from today forward, or actually today, is you should have, if you did the homework, you should be comfortable with your review of linear regression, just kind of connecting some dots. You also should have got a nice little review of z-scores and probability. Again, this is the last section that we cover in this class. You should see a lot of things kind of coming together. I was talking to somebody at lunch, I think it was, and I said, hey, you know, at this point, this stuff should be, once you see it, once you be like, oh yeah, that's right, I remember how to do it. It shouldn't be, oh my goodness, I remember we did that once in class, and I completely forgot how to do it. That's where we want to be is, I remember how to do it, I just need to study a little bit. You're in the right spot if that's the case. If you don't remember it all and it looks like a foreign language, we are going to be in trouble because your final exam, you're going to have some trouble on it if that's the case. All right? How many of you guys are continuing to look online at those old AP release questions? Anybody? A couple of us? Okay. Good. That will pay off big benefits. I hope that you guys are also reading the scoring rubrics for that as well as the responses. Have you guys checked those out for those of you guys that are doing it? Okay, there are responses there from students that will tell you scores. This is a 1, this was a 2, this was a 3, this was a 4, and here's why. Okay, so again, we'll look at that a little bit more next week. All right, today is going to be really, I call this a MUT test. M-U-T. And that stands for Model Utility Test. Okay? Model Utility Test. That's a MUT test. You'll use it on lines. In fact, when we talked about linear regression, the big thing is, the whole connection is, getting data and hopefully getting some sort of linear relationship so that it predicts that value. And we use an x value to predict a y value. And we use it to estimate, or we use it to model things. As this goes up, this goes down, or as this goes up, this goes up. And we predict. So model utility test, this really says, is this a useful model or not? And the way that we kind of look at it in terms of statistics, and it should make sense to you guys as students of math, usefulness in a line has a predictable change in y, change in x. It's the same every time, although mine doesn't look drawn to scale right here. A change in y over change in x. Do we have a slope or do we not have a slope? Because if we have a slope, then we have a useful estimator. If our line I don't know, that might have a positive. If a line has a slope of 0, would we agree that's not a useful product? That y is constant. It doesn't matter what x is. X is not going to predict anything. Does that make sense? So remember that horizontal lines have a slope of 0. And any line that is not 0 will have a slope. So in this case, connecting ideas of usefulness of slope and our hypothesis test, then think about evidence. Our null hypothesis is really going to be that slope is 0. We're going to assume that the slope is 0. Unless we have evidence to say that the slope isn't 0. And if the slope isn't 0, we would take that as convincing evidence to say that that is indeed a useful model. Does that make sense? Okay? So connecting 2 or 3 dots. I'll kind of get the fine parts right now, and then we'll get to it. I think today is actually a little bit easier than yesterday because it's more recent than the stuff we've done. So in this section, we're concerned about the slope of population regression line. Recall that the regression line is used to predict values for the dependent variable. The dependent variable being the y variable. The slope that we get from the least squares regression line is just an estimate for big B. We talked about that yesterday. Possible values of B are summarized below. These are just the assumptions again. Notice if you see things that show up here, they've shown up in other places. The mean value of lowercase b is B. That means with repeated sampling. This linear regression model works just like all the other models that we've done in class. Just like as we sample for x bar, we use it to predict mu. Just like p hat, we sample to predict capital letter P. And what I said was, long ago in a galaxy far, far away, with repeated sampling, and do we agree that if I sample, I'd get an x bar once with the standard deviation from that sample? I'd get another x bar from another sample. I'd get another x bar, I call that x bar 1, x bar 2, x bar 3, x bar 4. And I could repeat those samples, correct? And then if I average these samples together, that would become a very good estimate of mu. In fact, that was one of our very first assumptions, that the average of my samples is what the true population average is. Same thing here. The mean value of our lowercase b's, or the average of our lowercase b's, are the average of all of our samples, because if we all, and right now if I made all of you guys little mini statisticians, and I said, hey, we're going to go gather data about the exact same situation. And the situation I'm going to have you guys gather is this: hours of sleep last night and GPA. I happen to think that there is a direct correlation, or there's a linear relationship between the number of hours you sleep and GPA. I know that that's not right, but I'm just saying, go with me on this. So I send each one of you guys, there's 30 of you guys in class today, I think. So there's 30 of you guys. I send each of you guys out, and I'm going to say, you guys are going to randomly sample from our school. Agreed? There's a big population of 1,800 students that you're going to sample from. You go to Miss Suka, our registrar. You have randomly sampled with your calculator. What do we want to say? I make you guys sample 100 students. Okay? Do you agree that most of you guys would have separate students? Some of you guys would have the same student, but most of you guys would be separate. You guys agree with me so far? And you go and find, you sample those kids. And you said, how many hours of sleep did you get last night? And what's your GPA? And assuming that we have that information and that it's honest, wouldn't each of you guys then have 100 relatively unique data points? X, comma, Y for hours of sleep and GPA. That means, couldn't each of you guys in your little calculator then put your 100 data points and create a linear regression model? And if you're with me so far, wouldn't all 30 of your guys' linear regression models be just a little bit different than each other's? You guys would have a different y-intercept and a different slope. Would all those y-intercepts and slopes be close to the same thing? Does that make sense? So then if I averaged all your slopes together, all 30 of your slopes together, then I would have a very good predictor of what that slope really is. Does that make sense for the repeated sampling component of it? Whose mean value is that? Okay? And then we get thus, that is to say that the average of all of our samples of B would equal capital letter B. Thus, we have lowercase b is an unbiased statistic for estimating B. That's all right. That's just word. You don't have to memorize it. Standard deviation of the statistic B. This should make sense for you. Standard deviation of your sample will be the standard deviation of your population divided by the square root of SXX. And I'll talk about what that is right now, and we're in just a second. Yeah, it's I'll talk about this in just a sec, so don't worry about it. It does say the square root of s and then xx, and I'll say what that is in just a sec. However, this formula is not practiced for inferential methods since sigma is unknown. When we see sigma is unknown, that tells us it's what kind of test? T-test. Okay, we have unknown sigma. It's a t-test. Therefore, we will use this SB, which is standard error for slope. That is standard error, which we get from your guys' model, divided by the square root of SXX. And I told you, I'll explain what the square root of SXX is right now. That is the sum of all the x values from the average squared. Okay. X minus x bar squared. And that's our estimated standard deviation. And this really, right now, as I'm talking about it, should be clearing cobwebs out for you because we've talked about these exact same things just under different data sets. This is just linear regression as opposed to an X bar. And hopefully you're seeing right now as I'm talking about these things as to why we're going to use T instead of Z. Lastly, number 3, the statistic has a normal distribution. Again, we'll get into that in a second. Big takeaway from all this, realize that we're using a t-statistic because sigma is unknown, and this is the standard error for slope. Yesterday we had the standard error for the linear regression model. This is the standard error for slope. So this is just talking about slope. All right. Confidence intervals. We're going to do two things, just like we can do confidence intervals and hypothesis tests for all of our other statistics. We'll do a confidence interval and hypothesis test for this. And oh me, oh my, I'm shocked to see it will behave almost like the other ones. It will be little b plus or minus t crit times, so the standard deviation, oops, don't want that. The standard deviation of slope. Okay? There's actually little to no work for that, standard deviation of slope. T is based on, and we've got n minus 2 degrees of freedom. I just remember degrees of freedom. This one, n minus 2, we have an x and a y. It's bivariate data. N minus 2 is degrees of freedom. Okay. Hypothesis testing still can be two-tailed or one-tailed. Is there evidence to say that the slope for this model is positive? Then we're going to be testing for greater than. Is there evidence to see that it's greater than? Is there evidence to say that the slope is negative? Is there a negative relationship? We're going to go B is less than. Is there evidence to say that there is some relationship for slope? In other words, is there a relationship here or not? Then that would be a not equal to. Okay? Two-tailed test. So null hypothesis will always be H sub 0. B equals the hypothesized value. I can't spell that. And then our alternative will be one of those three. The model utility test. The model utility test always is saying slope against 0. Okay? So if you see the words model utility test, it's going to be your hypothesized value is 0 and you're going to check for not equal to 0. Another way you may see a test for slope, you might see something like this. Is there evidence to say that the slope is greater than 3? Does that make sense? So then this would be equal to 3, and it'd be a one-tailed test for b being greater than 3. Does everybody understand what I'm talking about there? Okay. All right, assumptions. At this point, you probably know them. I'm not super concerned with the front two. The bottom two are the ones I'm more concerned about. Distribution of E at any particular, that's the air, at any particular x value, has a mean of 0. Again, I'm not super concerned about that one. Standard deviation of E is denoted by sigma. Also not concerned about that one. 3 and 4 are the ones that I want you to know. Distribution of E at any particular value of x is normal. This is an assumption. You're going to say that those errors around any x value are normal or approximately normal. And random deviations associated with different observations are independent. Notice that we have random, independent, and normal. Okay, make sure you're able to put it in the correct context. In this case, we're talking about the variation, the deviations there are random, and each one is different or independent at one x compared to another x, compared to another x, compared to another x. If you did print up your notes, you're going to see the next slide. I'm going to be talking about this point right here. Distribution of errors. Errors, do we agree that an error is kind of that actual value compared to its predicted value? That's how far it's off, right? Sometimes it's above, it's over-predicted, sometimes it's under-predicted. You remember this in the context of residuals. So, when we're looking for normality, we're looking at the residual. Wait, hypothesis test. I skipped a point. I'm ahead of myself. Sorry about that. It's hard for me to read these notes. Hypothesis test that we were making about is whether or not the regression line is a good predictor or why. This is referred to, and I've already told you this, the model utility test. Anytime you see model utility test, we're testing to see if there is a slope. Okay? A slope of 0 is not useful. A slope that is not 0 is useful. Model utility. Is your model useful or not? Okay? And again, I already kind of gave this to you and showed it to you. So our null is equal to 0. Alternative is not equal to 0. Make sure those are capital letter B's because we're talking about the true slope, not the sample. We okay on this? Not yet. Bottom part? Top part. Pop your class today. All right. Quick review. You will see this kind of output on your AP exam. I guarantee it. I actually am at the point, I used to not like it. I used to like to have the data to put in my calculator. At this point, I actually would much rather see computer output given to me as opposed to putting it in my calculator. You need to know where this information is. This is yesterday's AP yesterday's information on when we stepped through rubber bands on babies and predicted IQ. This was the equation that we came up with. things that are given to you. I showed you guys these outputs earlier when we did chapter 5. And I said we didn't use a lot of this stuff. And we don't. This is SE, standard error. Remember yesterday, I think we got 17.49 something. Is that right? From the notes? R squared, you should know, interpret. Sometimes you'll see an R squared adjusted, ADJ. We never use the R squared adjusted. This part is the new thing that we will use. We're using it for our hypothesis test today. The standard deviation of the slope. Standard deviation of the slope. Coefficient is the number. Here's the predictor constant. That's our y-intercept. And cry count. That's our x value. That's what's changing. That's your y-intercept, and that is your slope. Standard deviation, all this stuff for the y-intercept we don't use. I've never seen them asked about it. We don't use it. And, whoa, that's kind of cool. Today we'll talk about that and that. And based on what you know up to this point, what do you guys think about a t-value of 3.07 and a p-value of 0.004? It's a t-statistic, and it's an actual p-value reported for that t-statistic. So your output of the hypothesis test is actually given to you here. Does that make sense? I'm going to show you how we calculate that t-stat in just a sec. And I'm going to show you how to do it with an actual data set. So we're going to go there. But this is also why I like the computer output better than having to do it in my calculator. Because if I have to do it in my calculator, I have to press all the buttons. This, I just need to know where it's at, and it's giving me all the answers. Okay? So here we go. Accompanying data on a 6-year graduation rate by percent and the student-related expenditure for a random sample of undergraduate public universities and colleges in the United States with their enrollments between 10 and 20,000. So in other words, these are a random sample of colleges, the number of students that attend them, so they're pretty large, between 10 and 20,000 students that go there. This is how much money they spend. This is old data. It's a lot more than that now. How much they spend per year. Student-related expenses. So that's talking about going to college, paying for your books, eating, and somewhere to sleep. Okay? That's what it's saying for college students here. So at this school, it costs about $8,000 per year to attend. The graduation rate, the probability that you will graduate if you spend that much per year and go to that school is 49%. Okay? And for this school, if you spend $6,401 per year, at this school, that's the average amount they spend, and that's their average graduation rate. That's probably that you graduate in 6 years. What we're looking to establish in this relationship is, can you, quote, buy your degree? In other words, the more I spend, the higher the probability it is that I graduate. Do you see that that's the linear model I'm looking for here? Okay? So we're going to use expenditure, that's x, that's our independent variable, and we're going to use that to try to predict our y value. Okay? So you guys go ahead and get this down in your calc, and we're going to go from there. All right then. Make sure your data matches mine. Let's see. Create a linear model given and comment if it's appropriate model. Let's see. Hopefully, you guys get something like that? You guys match? Okay. No? How many people raise your hand if you match? Okay. So I'm thinking that most of us are correct. So if you don't match, you have a data input error. Okay? Should look something like that. in, let's see, the linear model should be, I think I'm going to do this. Rerun mine. And I'm just going to do this. We're going to go. Okay. So there's our information. What do you guys think? Linear model appropriate? Weak? Okay. Let's do this now. Oh, I'll go here. Let's do the 95% confidence interval. Okay? 95% confidence interval for this is going to be, I guess I should specify confidence interval for slope. Because today we're looking at slope specifically. 95% confidence interval for slope is going to give us, remember, it's capturing or not capturing the true value of big B, or the true value of slope. So in this case, that's going to be lowercase b plus or minus t crit times the standard deviation of slope. In this case, our estimate for slope is 0.00468. Okay. Plus or minus, we don't know what SB is yet, but we can get the T crit. This is a 95% confidence interval. How many pieces of information did we have there? 15 pieces of information. So we have 15 minus 2 degrees of freedom. We have 13 degrees of freedom. We need the T crit at the 95% confidence interval. You can get that off your formula sheet, or you can inverse T it. I don't happen to have that memorized. We need to inverse T 0.025. And then your degrees of freedom, which is 13. T crit there comes out to be 2.16. Do we agree that the only thing we need at this point is the standard deviation of slope? And here's one of the best buttons that I have for you ever, because you saw how much that formula was, and most of you guys already predicted it, and some of you guys even started looking for it already. Stat, test. At the very bottom, we have, oh me, oh my, I'm shocked to see, a linear regression t-test and a linear regression t-interval. Linear regression t-interval. Where is your x data? List 1. Where is your y data? List 2. Frequency stays at 1. Confidence level 0.95. Hit calculate. Here's why I think this button's awesome. It gives you the confidence interval. It gives you the linear regression model right here. It gives you the degrees of freedom. It gives you the standard error for slope. That means you don't have to calculate it by hand. Question? Oh, TI-83s don't have it? Oh. You don't have the interval, or you don't have it either one? There's a t-test? Okay. Go ahead and hit the t-test, because you can pull, the t-test will also give you that 8.4 too. Go ahead and hit the t-test. If you do not have it, if you're using a TI, what is it, 83? If you're using a TI-83, then you need to go ahead and hit the hypothesis test for it. It will still give you the standard error for slope. It should come out to be 8.426. Is that right? Okay. We're good? What did we get there? That's standard air. And 0.426. Okay. Let's see, in our confidence interval, okay, Mick, I got to come back because that's not our standard error for slope. That's actually our standard error overall. That interval came out to be negative 0.0009, comma 0.0103. Okay, and that is from your calc. I got to do one more thing for some of you guys because this is standard error, not the standard error for slope. I thought it gave you standard error for slope, but it does not. So I got to show you guys how to calculate that one. That's a hand calc. Most likely, again, I've never seen them ask you to hand calc this one, so I'll show it to you. But I'm not concerned that you memorize it. What's that? Yeah. Does it do it in that one? But it doesn't do it in this one, right? Well, what version is that? You got an 89. So the 89 gives you standard error for slope. So if you also have one of the Inspires, it'll give you standard error for slope. So this one doesn't. And if this was an actual AP exam, I would just do this. That's what I would do. And then just put and report the interval. I'd be willing to bet you, and I actually, I'll show you how to calculate the standard, this square root of SX, you're going to have to go in your calc and do. That's the sum of X minus X bar squared. If you want to do that, you got to go here, stat, edit, and we got to go, I got to average X bar. So we got to go 1 bar stats in list 1. Just to find out what X bar is, it's 6,478.53. 6,748.53. When you're editing, we've got to make list 3. You need to make it list 1. Oops, I'm going to make it. We need parentheses list 1 minus X bar, which is 6,748.53. And we've got to square that. It's the X values minus the X average squared. That will be a big number. And then we have to sum it. So we need to sum list 3. It's a big number. Okay, that's the number. And then you need to square root it. Your formula, it is standard error divided by that thing we just did in our calculator, which is the square root of the sum of X minus X bar squared. So I'm going to kind of just do that in one step right now in my calc. It'll be 8.42, what was it, 61? Divided by the square root of that answer. Okay? And that'll get you, now, that's the standard error for your slope. Yes?
So if you have a TI-83,
If you have TI-83, I'm going to tell you, they're not going to expect you to A, memorize this and do a hand calc. Okay? Well, that's just why I'm saying more and more frequently they're giving you the outputs. Because this is listed for you right there on the output.
well,
Yes?
let's for example, the test tomorrow.
Test tomorrow. If it is on the test tomorrow, then I'm fine if you just put that for a confidence interval.
So I would have to do a conference.
Yeah, if you can take it all the way up to that point, that would be fine on the test tomorrow.
Because there's no.
Because you can't do that without doing this part. And I'm fine with that. And I honestly can't remember if I asked you to do that or not, because I did rewrite some of it, but I don't remember if I wrote that. Used to be the catch is, like everything, it's evolved, right? So it used to be they wanted you to calculate this stuff by hand to demonstrate your competency. Now they're like, no, we don't want you to waste your time calculating this by hand. We want you to know what it is you're talking about. So that's why, for you guys, I try not to focus too much on this computational stuff and say your calculator's going to do it, but it's way more important for you guys to understand what your calculator's doing than doing the calculator. Used to be students were like, man, I can get an A on this. I can pass the AP exam just because I know how to work my calculator. That's not it anymore. It used to be it, as long as you knew how to work your calculator, you get an A on the AP. You pass the AP exam. Now it's a lot more, what does this stuff mean? Not can you do it, because they give you it. Does that make sense? So anyway, there's your confidence interval. Interpreting it. I think we finally got that standard error, which is a mess of a calc, 0.002574 rounded. And notice that what number is caught in this confidence interval. We are 95% confident that the true slope will be between the value negative 0.009 and 0.0103. Same wording of our confidence intervals that we've always had. 0 is captured in that confidence interval. 0 is captured in that confidence interval. We essentially kind of have a high probability of, or a very realistic or probable value of the slope being 0 there. Which means this is not a very useful model. Does that make sense? Okay? That's confidence interval for it. The other way that we're going to do it is a hypothesis test. And this is the most common way that I've seen it asked on the AP exam. Perform a model utility test with that given data set, or perform a model utility test given that computer output, or is there evidence to say that the linear regression model is a useful model? Okay? You're going to come back to the hypothesis test. Same 8 steps as we always have. Step 1, same data sets are in your calc. Step 1, tell me what it is you're talking about. B, capital letter B. We're talking about the true average change in graduation rate associated with an increase of $1 in student expenditure. Again, slope, change in y over change in x. We have a change in graduation rate compared to a change in spending. X is our spending, y is our graduation rate. 2, null hypothesis. We're going to assume that the slope is 0. Step 3, alternative hypothesis. We'd like to see evidence of the slope not being 0. In other words, we'd like to see evidence that the slope has some sort of usefulness. Does it say significance level of alpha 0.05? We'll do that. That was step 4 there. Step 5, name the test you're doing. This is a linear regression model utility test. And this is what, yep.
Can we abbreviate that as much on the AP exam, or just write it all the way out?
Write it out. They will probably script you model utility test. In other words, they'll say perform a model utility test. This is where we talk about random, independent, and normal. If you have an actual data set, I'm going to kind of do 2 things here. Actual data set here's what you need to do. Show residual plot. If you don't have an actual data set, if you have a computer printout, look for random, independent, and normal within the problem because there's no way to check your residual plot. Okay, if they give you a computer printout and they don't give you a residual plot, then you need to look for in the problem, does it say that it's random? Does it say it's independent? Do we say that we have reason to assume that's normal? Okay? If they give you a residual plot with the computer printout, all you need to do is refer to it. Again, all of these are met if your residual plot doesn't have the patterns in it. So once again, looking for patterns in the residual plot. I'll tell you that this residual plot, some of you guys may have done it already. Actually, I can throw it real quick. I'll put it up here. The residual plot for this data set. Just change your y values to the residuals. And I got to take my y out. And zoom stat that. Your residual plot should look something like that. Doesn't have any patterns in it. You guys are good. Okay? So, if they give you a data set, just sketch that residual plot saying it doesn't have patterns, or talk about patterns within it. You justify or you match your assumptions by referencing the residual plot here. Watch, we are almost done. Step 6, we're going to use a t-test for this, and that is going to be b minus capital letter B over standard deviation of B. Which in this case was 0.0047 minus 0 divided by that 0.0026 that we calculated. And once again, this will be done for you. Stat, test, and this sounds like this one is in everybody's the linear regression t-test. Not everybody has the interval. List 1 is your x values, list 2 is your y values, frequency is 1. We're looking for not equal to 0. Calculate. And I was hoping that they might give you the standard error for your slope, but they don't. So, we need to use the t-value here. They do give us the degrees of freedom, notice it's 13. It does give us a reported p-value of 0.09 and a t-statistic of 1.82. So we'll report the 1.82. With 13 degrees of freedom. That p-value, and I can't remember what that was, 0.02, 0.09? 0.09 to 1. I'm moving into step 7 now. 0.09 to 1 is greater than our alpha value, which is 0.05. 0.09 to 1 is greater than 0.05, so that's going to be fail to reject the null hypothesis. And step 8, we are 95% confident that there is not, question? Enough evidence to say, we can say there is a useful linear relationship between expenditures and what was our other one? And graduation rate. Thank you. Yo.
Where'd you get the point or
0.0026. That's what we worked for that big long calc. The one we did here. We did that in our calc. The 0.0026 is coming from that. I have not ever seen them ask you to calculate that by hand. Yeah, if you do that all the way up, then I think I'll double check the test that you guys are looking at. I don't think it's going to be. I don't think I'm going to have you guys do that.
Yeah, but don't we need
Or I will tell you this, I might tell you what that is. I might provide you what SXX is. And if I do give you what SXX is, then I do expect you to be able to calculate that. Do you understand what I'm saying? Like, I mean, that came out to be a really big number. I don't want you to calculate that, but I want you to be able to take that number and divide it by that number. Does that make sense?
So if we don't need this number, how are we supposed to plug it in for the hypothesis test without calculating it?
I've seen them provide you with that number. That's what I was just telling Brenda.
Okay.
So this you can get from the calculator output.
Mm-hmm.
Everybody can get that from calculator output. It takes work, but everybody can do that part from the calculator. I don't want you to waste your time doing that part. I will provide you SXX.
Which is the same thing as SB.
No, to get SB, you need to take the standard error, divide it by the square root of SXX.
Okay.
Make sense?
Yeah.
Okay. All right. That's it for model utility test. That's it for linear regression hypothesis tests.